Now, I will discuss few more advanced program. This is a CPU vector addition program. So, first of all I have defined, you can see here that the size of the element, this much of the size of my vector, and I am using the float type. You can check here what are the value I am using, it is a float type, this number is a float type. So, I am just considering that it is a float 32. So, size of the element means how much of the memory is to be reserved for this is going to be this into 4, because each float 32 will take 4 byte of space. So, we have a n this much of element. So, you can understand that. So, this much of space is required. If you count it roughly, it is 40 MB space is required to store one element. So, I have 3 elements, 3 variables. I have 3 variables. So, in 3 variables, and each variable need 40 MB of space to store this many of elements. So, you can see here that it is the allocation of memory, and you can notice that I am using the malloc function of standard C++. So, that means this allocation is happening at the CPU's memory, CPU. After that, I am initializing A and B values here. A is initializing with 1.0 and B is initializing with 2.0. And here you can see the vector function which I have declared here. This is my vector function, vector add, it is a CPU vector add function, right. After the addition function is over, I am just using the free function of standard C++ to make whatever the allocation I have done. So, total I have reserved around 120 MB of space in a RAM. So, when I use this free A, B and out, so that means all this 120 MB of space will be released. Now, the same vector program I will discuss for the GPU vector addition. So, you can see the number is same, but additional thing is that these are the two addition. Why this two addition? Because we know that if you want to launch the kernel on GPU, you have to tell that the number of blocks you want to launch and how many threads in each blocks to be launched. So, these two information we have to pass in a GPU kernel. So, that is the reason these are the two additional parameters we have defined. You can check that in a CPU vector addition program it was not there. Now, I have defined the global, use the global qualifier. So, now we have a complete understanding that whenever I am using this word, that means this function is a kernel now and this should be launched on the underlying GPUs. If you look at the logic which I have implemented here, it is same for GPU as well, GPU and CPU. The logic is same, addition logic is same, there is no change. Now, I have come to the main operation. So, first I have declared some pointers for the host memory, because now I have a device, a GPU, and GPU also have some memory. So, that is the reason we have to declare the another variable for the GPU's memory, we call it device pointer. Now, memory allocation section. If you come here, this is a malloc has been used here. So, you know that whenever I am using the malloc is a standard C++ function, and memory is allocating on the host memory, means CPU's memory. Total size is going to reserve is 40, 40 and 40 MB. So, total is 120 MB space is reserved for all three variables or all three arrays, you can say. In this portion I am just same function, initialization function, which I have used for the CPU vector program, same initialization function I am using for the using in vector addition program. This is the addition in a GPU program. So, you can see here that after the allocation in a CPU or host memory, here I am doing the allocation using the CUDA malloc function in GPU's memory. After this allocation, this is also of same size 40 MB, 40 MB and 40 MB. In case you accidentally declare the space more than the physically available space on the GPU, then it will start throwing the error in a compilation time itself. After allocation of the space in a CPU and GPU, it is a time to transfer. This is also two additional instructions here. This is a time to transfer the data which I have initialized in a host system to the device memory. So, you can see these are the two CUDA mem copy functions, and I am copying the data. Which variable I am copying? I am copying the data A to data to D underscore A, data B to the variable B underscore B. The direction size, you know that what is the size here, and direction is host to device in both cases. After that, we have to call the function, because we have to launch the kernel. This is a kernel launch function. So, whenever I want to launch the kernel, I have to pass number of blocks and size of the block, and here I am passing the inputs. So, you can see that how I have defined my function, kernel function. When I define this function, I have passed input, input, output. So, you can say output, output, output and size. So, these are the input things which I have passed to the function. The same you can come here and you can see that I am passing the 4 parameters to this kernel function: out, D underscore A, D underscore B, because my data is available at D underscore A and D underscore B. Here you can see that. So, A is a variable that is present in a host machine, D underscore A is a data which is available in a device memory. So, data is available under D underscore A and D underscore B, size is a constant, we know that, and D will be the output of addition of these two variables D underscore A and D underscore B. When this operation will be executed, kernel will complete its operation. So, we have data final result is available under final result is available in the variable D underscore out. Now, the D underscore out values to be transferred to the out variable. The out variable is available in a host machine. So, that is the reason the direction will be device to host. After copying the data, you can apply this logic. This is optional. If you want to check the correctness, so you can apply some logics here. You can check few results for the correctness. After the completion of all executions, it is a time to free the space which has been allocated on the host machine as well as on the device. So, here it is you are freeing or you can releasing the space occupied on the device memory, and this function you are using to free the or release the memory space on the host machine. Now, I will discuss about the unified memory concept. So, pictorially you can see that each host machine has their own system memory. A device, this is a device, means GPU, it has its own GPU memory. If I add one virtualized layer over these two, then it's become the unified memory. So, meaning is that device does not know it is my memory and CPU does not know it is my memory, both are treating as a unified memory. So, whatever the data is to be is required, so device can request, and because it is a unified memory, and device can access this memory with the help of some pointers. So, unified memory in CUDA is a memory management feature that simplifies the programming model by providing a single memory space accessible by both host and device. And it allows the developer to reduce to allocate the memory without worrying about the transferring the data between CPU and GPU explicitly. In a previous example, you have just seen that we are allocating some space here. Here you can see that we are explicitly allocating some space on CPU, and here I am allocating some space on GPU. So, if you are using the unified memory concept, so you need not to worry about such allocation explicitly. So, what is the concept of unified memory? So, it is providing the single address space, means unified memory provides a single address space for both host and device, allowing the pointer to use interchangeably. Automatic data migration, whenever the data is required by the host and device, the data can be transferred. Page fault, when GPU accesses a page of memory that is not currently on the device, then page fault will occur, and whenever this page fault will occur, the host machine will trigger a data transfer from its own memory to the device memory. Memory allocation is a concept here. So, memory is allocated in case you are using a unified memory concept. So, you have to programmer have to allocate the memory using this keyword or this function CUDA malloc managed, which returns a pointer usable on the both host and device. In terms of performance, while unified memory simplifies the memory management, it introduced some latency due to the data migration and page fault. So, it has some advantage and associated with some disadvantage as well. So, it is a need, it is a totally depends on the developer whether he wanted to use and whether he is actually gaining the any benefit by using this memory this unified memory management concept. So, he can use it. There are some APIs which are which should be used for the unified memory concept, or you can say unified memory allocation. So, first one is a CUDA malloc function, CUDA malloc managed function is a API which allocate the managed memory that is accessible from both host and device. Then the same CUDA free function, this function is used to release the memory space that is allocated with the CUDA malloc API or function. CUDA device synchronize, it waits for all the pending commands on the device to be completed, which is synchronizing the operations. CUDA memory get info, it retrieves the amount of free and total memory space available in the unified memory. Next API is CUDA mem advice, and this provides a hint to the CUDA driver about how the memory will be used and which can optimize the performance. Next one is a CUDA pointer get attribute, and this API retrieves the attribute of the pointer such as whether it is managed memory or the device memory. So, what are the pointer is being used? So, you must have an idea whether it is belongs to the managed memory or device memory. So, such kind of information you can get related to any pointer by using this API. Now, I will discuss about the shared memory allocation. So far I have discussed about what is a shared memory. Shared memory is a space which is accessible by the block, or you can say all the threads within a block, and it is sharing the space with L1 cache. The shared memory allocations can be done by two ways. The first one is a static shared memory allocation, and second one is a dynamic shared memory allocation. So, you can see the static shared memory allocation. So, how we can define the static shared memory allocation? So, you can see that I have used the qualifier shared, then I am declaring some name of the variable and its size, that is around 256 byte. So, where the static shared memory must be used, and it must be used when the size is known at the compile time. When the size of the shared memory is known at the compile time, and it will remain constant throughout the execution of the kernel, not of the block. Throughout the kernel it is going to be a constant. As I already discussed that static memory allocation has a limit of allocation. It cannot be allocated more than 40k kilobyte of shared memory. If you are using, by any chance you are trying to declare it more than 48 kilobyte, and it will throw the error at the compilation time itself. You are using too much shared data. And this shared static memory allocation is very much useful if the fixed number of elements are to be processed, and you know it well before the execution of your program or application. Now, I will discuss about the dynamic memory allocation. So, you can see that how we can declare the dynamic. So, here we have to use another term extern to be added just well before the shared qualifier, and after that whenever you are declaring any name of the shared variable, no need to define the size here. So, that means is a dynamic allocation. While the program is executing, it automatically compute the size of the data, shared memory data to be created at runtime only. So, that means when in a compilation time programmer does not have any idea about what is the size of the data and how much of the size of the shared memory is required at compile time. So, that means whenever it is executing, so that means at runtime the size will be defined. At runtime, suppose you need a 32 kilobyte of space or 20 kilobyte of space, whatever the space is required, it will declare accordingly. So, that means it is very much useful when the size varies. An important note is that the specific shared memory limits per block can vary depending on the architecture. So, if you want to see the what is the size of the shared memory will be supported by the particular GPU architecture. So, you have to refer the manual, or you can use the device query functions to get the information about that, how much of the shared memory you can allocate.